I'd like to welcome everybody to our second Exergen Global webinar. It's a pleasure to see you all joining today. The topic of the webinar today is our IRTC heat balance, non-invasive temperature measurements in medical applications. Let's start with a little bit of housekeeping. We're going to hold a presentation of about 30 minutes today, explaining about the webinar, about the IRTCs, medical applications. After the presentation, we will have a question and answer session. There's a toolbox at the bottom of your screen with a Q&A button. You can type in your questions. If we have the opportunity to answer them during the presentation, we will do that, but it's most likely that after the presentation, we will go into the questions and answer your questions. We would like to round off at after about 45 minutes. Should not all questions be answered, don't worry. Any questions that we did not manage to answer during this webinar, we will get back to you and answer your questions by email. Also, after this webinar, feel free to contact us for any questions you might have. It's still, hopefully almost the end of the pandemic, where in the near future, traveling will be more easy and we can travel freely again. In that case, if you have projects, if you have questions, we would really be happy to visit you and to assist you in a more personal meeting. But for now, this digital way is a very pleasant way to interact with you and to hopefully have a very interesting and educational session on non-invasive temperature measurements. We'll start with telling us who we are. I'll kick off myself. My name is Bram Stelt. I am the CEO of Exergen Global as of 2019. I've been working for Exergen Global for over 10 years now, so more than 10 years experience in the infrared sensor market. I have a background in biomedical engineering. So I actually started working for the company to explore applications of the sensor technology in medical applications. So the topic of the webinar today is right up my alley, and it's something that I enjoy doing a lot. I think it's very interesting, and I hope I can teach you about this very interesting field of applications. I'm located in the Netherlands. That's where our global OEM sales office is. So it's 8 p.m. now. Again, welcome everybody. And my co-host today is Bob. Bob, please introduce yourself.
Thank you, Bram. Thank you for putting the kids to bed early so you can be here for us. And I'm Bob Harris, Sales and Marketing Manager here at Exergen Corp. I'm here at the factory in Watertown, Mass. My background is in electrical engineering. Went to Northeastern University. And about 30 years ago, I worked a co-op job at a company called Abiomed. And they made this machine called the BVS. And what the BVS was a piece of equipment that actually took the place of a heart for artificial heart patients and for patients waiting for heart transplants. And it was pretty exciting, at that time to see a product such as that. And what they did was they brought in caps, and they were, using caps in the labs to, to pump blood in, and, using the machine as the heart to keep the caps alive. And now 30 years later, working with Bram and my colleagues at Exergen Global on these medical applications where we're doing similar applications where we're using medical technology in our IR sensors to measure the temperature of anything from blood running through a tube to skin temperature to body temperature to detect fever. So everything's kind of coming full circle for me, my career here at Exergen, and looking forward to doing this presentation for you all, and looking forward to hearing your input, because that's what we do. We all learn as we do these webinars, and it helps us to help you in the long run. Thank you, Bram.
Thanks, Bob. So a short summary of what we're going to discuss today. We will start with some basics, how an IRTC can be used to measure surface temperature measurement and what the advantages are of having an unpowered IR sensor. Then we will go to the heat balance principle. How can this be used to measure a core temperature or a fluid temperature instead of a surface temperature measurement? I will explain a bit about some medical applications, give some examples to give you a feeling how it can be used. And I'll have a case study where I will go more into depth of the application of these sensors. I'll tell about the advantages of why an infrared sensor has a lot of benefits over contact probes. We'll show you a movie on how to calibrate the sensors to measure fluid temperatures. We'll tell you some tips and tricks when you use them and calibrate them, and then we will answer your questions. But we'll start with some of the basics. Bob, please, the floor is yours.
Thank you. The first thing I want to talk about is how an object actually, every object will absorb energy and absorb radiation. And the combination of the amount of energy that the object will absorb is, well, the object will absorb, transmit, and reflect energy. So if you add those three components, you get 100%. And oftentimes there is zero transmission. So most objects that we measure, they're pretty solid. The only exceptions would be like a thin film or a semiconductor where there may be some transmission of energy. But most of the objects that we're measuring are either reflecting or absorbing energy. So if you add up those two components, the percent of energy reflected plus the percent of energy absorbed, it'll equal 100%. And once that object absorbs all the energy, the temperature will increase. And the amount of energy that's absorbed is also equal to the amount of energy that's emitted when that object is at steady state. And there's a term called emissivity that's in the industry, which is defined as the ratio of the amount of energy emitted compared to a black body. And a black body is a perfect emitter. So materials will either be low emissivity or high emissivity. And the low emissivity materials are often, the shiny metal surfaces, and they are very poor radiators. And the high emissivity materials are highly emissive, and they're good radiators. And also a coated metal would also be a high emissivity material. So those are the types of objects that we have the best luck measuring. Of course, we can measure anything, and every object will emit energy, and but the high emissivity are the best radiators. Next slide, Brown. Now, about back in the early 90s, Exergen found out in the industry, and we listened to the customers, and what the industrial world needed was an infrared sensor, not a pyrometer, but an infrared sensor that could be a drop-in replacement for a thermocouple. So Dr. Frank Pompey invented the product called the IRTC, which stands for infrared thermocouple. And the whole idea of the IRTC was to have a drop-in replacement for conventional thermocouples. So what we do is we calibrate an IRTC so that the millivolt output matches that of a conventional thermocouple. And the formula for a conventional thermocouple is a constant called the Seebeck coefficient times the temperature of the surface minus the temperature of the cold junction. And what a conventional thermocouple does, it actually measures the temperature of itself. And what a non-contact or an infrared thermocouple does, it will measure the temperature of the target rather than the temperature of itself. And what the Seebeck coefficient is, it's the electric voltage in response to temperature difference across that material. So when the target temperature is equal to the surface temperature, there will be no IR energy. So when the IRTC looking at a target is at the same temperature, there's no IR energy coming from that. So the only energy that you will see or will be measured in the readout will be the temperature from the cold junction only. So what we do is we calibrate these sensors so that C, which is the calibration coefficient, equals alpha, so that the millivolt signal out is equal to alpha times the temperature of the target minus the temperature of the cold junction, so that you can plug this IRTC into any conventional readout device that will measure a thermocouple. And the IRTCs are also built with conventional thermocouple wire so that you can also use the cold junction compensation that's often used in these thermocouple readout devices. Next slide. So here's an example. So on the left, we have a conventional thermocouple. As you can see, The conventional thermocouple measures the temperature at the junction. And we have a little display there that's displaying what the temperature is of that surface. So the IRTC on the right is aimed at that same surface and is calibrated at around 240 degrees, it looks like here, so that it can measure the same temperature that the conventional thermocouple is, in the same readout device. So the other thing that we do here at Exergen when we calibrate the IRTC is we calibrate to real world conditions. As I explained earlier, there are effects of the emissivity and the reflections that will affect what the target is emitting. And typically in the real world, you're not measuring black bodies. We're measuring things that aren't perfect emitters. So they could range, you could be measuring wood, paper, glass, ink, blood, anything that's high emissivity that is not obviously a perfect black body. So there are a variety of different emissive property, emissivity numbers for the different materials. So what we do is we calibrate on gray body targets, and we calibrate in ambient blocks that will compensate for the ambient reflections on real surfaces where the emissivity is less than 1. In other words, on the gray body targets we use here, they're 0.9. So when we calibrate the sensor, we're calibrating for the effects of the emissivity as well, so that it matches the millivolt signal out of a thermocouple at that temperature with the effects of the ambient reflections and the ambient temperature. So to take to the next level, we can also calibrate the sensor, so then rather than just measuring the surface temperature, we can calibrate for the core temperature. So in this example here, TC is the core temperature of that block. And as we know, the IRTC is going to measure the surface temperature, but we don't want the surface temperature. We want the core temperature. So what we could do is we can calibrate this sensor, because it all correlates. When the core temperature changes, the surface temperature changes. So we can calibrate that sensor so that it actually displays the core temperature rather than the target temperature. And that's one of the things we're going to talk about here and show you some examples later on in the presentation where customers are actually using this heat balance technique with a specially calibrated IRTC for heat balance. And a perfect example of a product that uses a heat balance technique is our very own Exergen temporal scanner. And what I have here is an industrial scanner, the old DX501, which measures surface temperature. Now the Exergen temporal scanner uses the heat balance technique, and what it does is it will scan across the forehead, and when it crosses the temporal artery, it will give you the core body temperature of the blood coming from the heart. And by scanning across the skin and over across the temporal artery, because the skin is so thin and it takes the peak measurement, it's able to give you the temperature across the temporal artery. So if I scan my forehead with my industrial scanner, it's reading low. See, it's 92 degrees. Now, if I want to know if I have a fever, and as you know, in the last year, we've been doing this quite often, trying to see if we have a fever, scan across my forehead, and I'm 98.3 degrees. So I'm feeling good. I'm healthy, and I can return to work now. So that's a perfect example of a product that uses the heat balance technique, and that's a patented technology that we have here at Exergen. So here's another example where we have on the left an IRTC going into a special tubing clip that's measuring the fluid temperature inside that tube. So as I said earlier, everything correlates. So you have the fluid temperature, and RF is the thermal resistance of the fluid. RT is the thermal resistance of the tubing. And TWTS is the temperature of the inner wall of the tubing and the outer wall of the tubing. So everything correlates. When the TF increases, the temperature of the surface increases. So by calibrating the IRTC, and what we do to calibrate is you just turn a potentiometer to calibrate it, and that'll give you the output and display the temperature of the fluid. It's pretty simple, and it's pretty much, like the algorithms that we have in the temporal scanner, and it's very widely used for a lot of the medical OEMs.
Yeah, thanks, Bob. And I'll get into some examples now. Maybe it's good to add that what you see here on the left side is actually in one of our IRTC models that has been screwed into a clip, and a clip is especially designed to hold a medical grade tubing, so that the tubing is exactly positioned in the field of view of the sensor. I'll explain a few medical applications right now of this heat balance. What you see here is a myocardial protection system. And this is a device to cool the heart during open heart surgery. So when a patient needs surgery on the heart, they stop the heart because a surgeon cannot operate on a beating heart. That would be too complicated. So they stop the heart. But if they stop the heart, there is no perfusion, there is no oxygen supply to the tissue. So there's a risk of tissue damage. However, cooling tissues counteracts that process. So if you cool a tissue, it doesn't get damaged because of oxygen deprivation. So this is a device to cool the heart during open heart surgery. And what you see here is you see a medical or a disposable cartridge actually that can be clicked on this device. On the back of this is one of our IR sensors that is calibrated in such a way that it measures the blood that is in the cartridge. So it measures through the wall of the cartridge, and it measures the blood to ensure that there is sufficient cooling to protect the heart tissue. The next one is kind of a similar device, but it's not to cool the heart, it's to cool the brain. This was only recently launched. It's a device that is used in patients with cardiac arrest. So again, if their heart is stopped, there is no perfusion, but there's also no perfusion of the brain, and the brain is especially susceptible to deprivation of oxygen. So you can get tissue damage, and of course in the brain that can be very bad. Through the nasal cavity, so there's a tube with fluid, cooling fluid, going in one nostril, comes back in from the other, and from the nasal cavity it cools the brain tissue. What you see here are two IR sensors, where again a disposable tubing cartridge can be clicked on in such a way that two tubes, so the inlet and the outlet, the in and the out, can be measured. And by measuring the delta T in combination with the blood flow, they know the cooling capacity of the system, and they can control the cooling of the brain. The next one is an ECMO system, extracorporeal membrane oxygenation. It's the medical term basically for supplying supplying oxygen to the blood outside of your body. This is used as a lung support. And this is a type of system that we have had a lot of inquiries for over the last year, because COVID victims, they have lessened lung capacity. So they have difficulty breathing, getting sufficient oxygen in their blood. So this is a device that can be used to support the lungs. It's also used during surgery. So it's not only for COVID, but also in a heart-lung machine to supply oxygen to the blood. But the blood that's going back into the body needs to be 37 degrees. So there's a heat exchanger in there to make sure that the blood is warm to 37 degrees. You don't want to go too high, because that can destroy the cells. You don't want to go too low, because that could cool the body temperature of the patient. Both are things you want to avoid. So this is one where our IRTC sensors measure blood temperature through medical tubing. This is more of a diagnostic device. It's called the Echo, and is used to separate cells. You have a lot of various cells in your body, and for diagnostic purposes, but also for therapeutic purposes, this can be gene therapy or cell therapy. sometimes a very specific type of cell needs to be separated from the rest. There are various techniques to do that. And nowadays, the most common are spinning them down in a centrifuge, or having a filter where you kind of filter out certain cells depending on their size. But these have a few downsides. First of all, they can destroy the cells that you want to separate. And second of all, the filters can get clogged. It's not very sensitive into what cells you can actually really separate very well from other cells. This is a completely new technology where they use a 3D standing wave. So it's an acoustic system. And in this 3D standing waves, you have crests, and in between the crests is where the cells gather. And based on the characteristics of the wave, so basically the frequency and the wavelength, they can select which cells to separate based on the size. And it's very elegant. It works very well. And the big advantage is that you don't destroy any cells. The cells are in a good shape when you kind of harvest them. Why is temperature needed then? Temperature measurement, that's because by supplying these acoustic waves, the sound waves, you supply energy to the fluid containing the cells, and it heats up the fluid. So they need to make sure that the fluid doesn't get too warm. So it's kind of an alarm system to realize if the temperature gets too warm, which could potentially destroy the cells, you get an alarm. So that's how our sensor is used in this way. This is the case study that I would like to present. This is the Thermocore 1200 rapid infuser. And as the name indicates, it can infuse blood very rapidly, up to 1200 milliliters per minute. That's pretty fast, and that's a lot. So this is used in very critical situations where a patient really needs a lot of blood. Think in trauma situations after accidents. It's used a lot in the military, but you can also think about women during childbirth that lose a lot of blood, aneurysms that are burst. Basically, patient needs a lot of blood or it's end of story. However, the blood needs to be 37 degrees when it's applied, because otherwise, on top of big blood loss, you also get temperature, hypothermia or hypothermia. That's also very dangerous. The blood will come from donors. It's donor blood that can come from a fridge. So then it's really cold. It's about 5 degrees. It can already be thawed in a thawing system. Then it's maybe room temperature or already close to 37 degrees. So it can vary. But regardless of what the temperature of the incoming blood is, the output needs to be 37 degrees. So in the system are two sensors. You see them here. These are our IR sensors. One measures the inlet temperature of the blood, the temperature of the blood that's coming in. The other measures the temperature of the blood that's going to the patient. And depending on what the temperature difference is and what the required blood flow is, the system calculates how much power needs to be generated or how much heating power needs to be put into the system to warm up the blood sufficiently. And especially the second sensor that measures the outlet needs to make sure that the blood is 37 degrees. Also, what you see here is that the sensors are integrated into the body of the system. And there is a cartridge that can be clicked on the system quickly, easily, that ensures that at the right location, the temperature sensors measure the tubes to ensure the good temperature of the blood. This can be done quickly. And again, here, speed is of the essence because there's a patient dying. So speed is really, really important. I also added a few non-medical applications. I saw in the list of registrants and attendees today that not everybody is coming from the medical field. Some are coming from other fields. I just wanted to demonstrate that the heat balance method can also be used in other applications, non-medical applications. As an example, in tire manufacturing, so tires are made out of rubber. Rubber is a fluid that when heat is applied, it cures, it hardens. It's called vulcanization. And that's a temperature dependent process. In order to make tires, they heat up the rubber, but they don't want only the, let's say, the surface of the tire to be in a good shape, but also the core needs to be in a good quality. So our IR sensors are used to measure also the core of the tires to make sure that the vulcanization process is done correctly. This is a climate chamber for solar panels. Solar panels, before they are brought into the market, need to be tested extensively because they need to function and they need to have a certain yield in various climates, various conditions. So these are tested very thoroughly. And in these climate chambers, the performance of the solar panels can be tested from temperatures, let's say from -30 all the way up to 60, sometimes 70 degrees. And they want to know the temperature of the black photovoltaic cells, so the black cells inside the panels to see how they perform. But on top of these cells is a layer of glass, and our sensors measure the cell temperature through the glass to make sure that they are in good quality and function well over various temperature ranges. Those were the examples that I wanted to show. There are more, but I think this gives a good idea of how the heat balance can be applied. I now wanted to explain the advantages of non-contact sensors over contact sensors. I see quite a lot in the medical industry that contact sensors are now used to measure fluid temperature. Non-contact, in our view, is better. First of all, sterility. If you supply anything to a patient, blood, it needs to be sterile. So you don't want to put anything in the blood that could potentially cause an infection or contaminate it. With our IR sensors, there's no contact with the blood whatsoever. The ease of use, as I demonstrated in the rapid infuser, if you install the sensors in the body of the device and you develop it in such a way, design it in such a way that you can click on a cartridge, it's really easy. Click and it goes. The sensors will give you good results and measure temperature accurately and reliably. Whereas if you have a contact probe, it always requires manual handlings, attaching it, putting it through valves. That's not easy to use. Accuracy is a big thing, especially if you use contact probes that you mount on the outside of a tube. If the contact is not good, because a contact sensor will measure its own temperature. So if the contact sensor is not a good representation of the target, if it's not mounted well, then you don't get a good reading. With IR sensors, it doesn't really matter if the distance is a bit shorter or longer. It doesn't need to make contact, so it's very, very accurate. Reusability and the price. A lot of contact probes that are used are disposable probes, so they're sterilized. They're used once, and after the procedure, they're thrown away together with the tubing systems. That's a pretty expensive way of doing that. Sometimes the contact probes can be re-sterilized, but that also involves a lot of costs. With our sensors, they're reusable. You build them into the system, and they work for the lifetime of the system. You don't have to replace them. You don't have to recalibrate them. You don't throw them away. So it's a big cost saver. Speed is quite a big advantage. Contact probes need to acquire the temperature of the target that they are measuring, and that can take a certain time. IR sensors, they don't. Our sensors have a 50 millisecond response time. So bang, bang, bang every time. Very fast response time. You get a reliable and accurate measurement. And then there's the advantage of the unobstructed blood flow. If you put contact sensors in the blood flow, it disrupts the flow. Cells can coagulate around the contact probe, and it can disrupt them. With an IR sensor, it's an unobstructed blood flow, so there's no risk of coagulation there. We now go to a video that demonstrates how you can calibrate an IR sensor to specifically measure fluid temperature through a medical tube. I hope your heart doesn't skip a beat if you watch this. It's pretty spectacular. Have a look.
My name is Bram Stelt. In this video, I will guide you step by step in installing and calibrating the heat balance IRTC in this live tech applications. The sensor can be calibrated to measure fluid temperature in the temperature range of interest. This can be done by adjusting the calibration screw of the uncalibrated IRTC. I will explain this calibration step by step. For the initial calibration, a reference sensor in the fluid is required. Step 1. Install the reference sensor in the fluid. Step 2. Install the IRTC and align to view the desired target. In this case, our convenient mounting clip is used to mount the IRTC on the tube. Step 3. Bring the target to operating temperature, in this case 38 degrees Celsius, as indicated by the reference sensor. Allow the sensor and the clip to reach steady state temperature for approximately 10 minutes. Step 4. Adjust the calibration screw until the IRTC reading matches the reference fluid reading. Step 5. Test if the calibration is accurate over the internal temperature range of interest by varying the fluid temperature. In this case, between 35 and 42 degrees Celsius. If the sensor follows the reference sensor accurately, the calibration is successful. Possibly, some fine-tuning of the calibration screw is required to increase accuracy.
So what you saw here was a pig's heart. Actually, this is a company that is located very close to our office in the Netherlands. It's a company that has developed a technology to keep a pig's heart beating in their system for over 24 hours, and that is used for training of surgeons of certain procedures or to test new medical devices. I think it's very fascinating and interesting, and they allowed us to do some tests and make this movie on their system with the beating pig's heart. Some tips and tricks on using this technology and doing the calibration. First of all, as Bob explained, the millivolt signal that the sensor generates is based on the delta T, the difference between the target temperature and the sensor temperature. If there is no delta T, there is 0 millivolt. And if you then adjust the set screw, nothing will happen. So you need a certain delta T for the calibration to work. Ambient temperature can affect the readings. We have ambient temperature compensation, so small or slow ambient changes will not affect the readings. The sensor compensates for that, but big fluctuations or very fast fluctuations like a temperature shock will affect your readings. So if you design a system with a sensor integrated, make sure the sensor is as thermally stable as possible to optimize the accuracy. An IR sensor will measure anything that's in the field of view. It will give an average temperature of all the objects in the field of view. Now, if you want to measure a tube, make sure that the tube completely fills the field of view of the sensor, because if not, if you have a very small tube and the sensor looks, let's say, around it, then that will also affect the measurement. It will be part of your temperature measurement. It's advised to take tubes that have a relatively thin wall compared to the flow area, because temperature changes in the fluid need to be transferred to the surface of the tube as quickly as possible. And if you have a very thick insulating wall, that's not the case. So thin wall tube is preferred when using the heat balance method. And once you've done initial calibration, as explained in the video, test it, and you can also do some fine tuning on the set screw to maximize efficiency within your temperature range of interest. So these are the tricks that we have. And with this, we come to the end of our presentation. Thank you all. I hope you enjoyed it. I invite you to ask any questions that you might have in the Q&A box at the bottom of your screen. I see some questions coming in. You can always send us emails with questions, or if you have any inquiries after this, we would be really happy to answer them. I see we have around 10 minutes left to answer some questions. In case we haven't answered your question, we will get back to you by email or telephone. Now let me scroll through the questions to see maybe some, because I see a few. Thank you. If I see some maybe that have that are the same. No, I'll just start from bottom to top. The question is, does the specific calibration work on various tubing types? Yes, it does. That's the answer. We have tested it. So as I explained, it works as long as you have a, let's say, a relatively thin-walled tube. Of course, most of these applications are medical applications where medical grade tubing is used. And there are a few tubing types that are very common. These can be silicon types or can be PE or PU. And we tested a lot of those. And actually the type of material doesn't make a lot of difference. The size does. So once you have calibrated the sensor for a certain tubing size and also tubing type, then that calibration will hold as long as you use that same type and same size of tubing. If you change the size, the calibration might be off. So you would have to recalibrate. But again, the material, what we have seen, doesn't have a really significant effect on the temperature measurements. Let's see. How big should the delta T be? Bob, can I pass that one on to you?
Sure. Well, the delta T, well, the bigger the better. You know, it could be a couple of degrees C. You know, ideally, you know, most of the time when you're looking at, you know, room temperature, which is around 25 C, and you're looking at, you know, human body temperature, which is 37 C. So that's, you know, 12 degrees C. You know, that's ideal. You know, 8 to 10 degrees C would be the best. But I mean, we could calibrate with just a couple of degrees C as long as there is a delta T. You know, obviously, you know, half a degree wouldn't be ideal and would probably be difficult to do. So the larger the better. And you know, you could, and for these applications, you know, and even some like Brian mentioned, there are some that are non-medical. You know, we've come across some like food and beverage industries where they're, you know, they're boiling water and the sensor's at room temperature. So something like that is, you know, much easier to do because you have more signal to work with. So, you know, the bigger the delta T is the better. We can work with, you know, very small delta T's, but it could be a difficult calibration to do. And the other thing that, you know, you need to look out for too is if it's a low emissivity surface that you're looking at, you know, that combined with the low delta T, you know, may also give you some challenges because you really don't have a lot of signal to work with there. So the bigger the better.
Thanks. Thank you, Bob. I see one of the participants, one of the attendees, he has JL as initials, raised a hand. So I think he has a question, but may I ask you to type in your question in the Q&A box, and then we will answer that one. Let's see, there are other questions. Yeah, it's a bit in line with a question about the tubing type. Can the heat balance method be applied to metal pipes, for instance, to measure chemicals? Bob, can you take that one too?
Sure. Yeah, I think it's kind of almost answered some of that question earlier, but metal pipes are, you know, difficult to measure. So you would have to coat that surface to increase the emissivity to measure that. And you would only have to put a small spot on the area, where the sensor is going to measure. So that's what you would need to do. Otherwise, without coating the surface of the metal, you're going to have a lot of reflective energy, and it just wouldn't have enough signal to be able to calibrate that. So, yeah, the answer is yes. It can be applied to metal pipes, but it would have to be coated. And even something simple like putting a piece of tape over the area, it will help increase the emissivity. So it's not anything, don't have to do, you don't have to send it out to be anodized or anything. Just a small spot on the area where the temperature is going to be measured would be enough to be able to calibrate that.
Thank you. Let's go to the next question. The question is, what is the effect of ambient temperature fluctuations on the readings? It's a good one, because I explained if you have rapid or big fluctuations, it can have an effect. Our sensors are designed to compensate for ambient temperature fluctuations, and especially the heat balance. The idea is that the heat balance, that's basically why it's called a balance, is balancing various temperatures, which is tubing surface temperature, ambient temperature, and then to calculate fluid temperature. If you have big ambient temperature fluctuations, it will affect the readings. We've had a customer that was designing a system, also cooling fluid, and they positioned the sensor next to the heat exchanger to cool the fluid. So that was kind of the exhaust of all the heat that was extracted from the fluid. So once the machine was switched on, a lot of heat was directed towards the sensor, so its temperature would increase rapidly. And that is, we're unable to compensate for that. So if you design a system, try to keep the sensor in a position away from any heating elements or cooling devices, and try to keep it thermally as stable as possible. And then small temperature changes, like if you go from inside an ambulance to outside and then in the hospital, that shouldn't be a huge deal, and it will also stabilize pretty fast. If you have effects of ambient temperature on the sensor, as long as then the ambient temperature will be stable again, the sensor will also stabilize and you will have reliable readings again. I think if I look at the time, we will go to one final question. Again, I saw JL raise his hand, but I don't see a question yet. So please feel free to send us an email if you have that question. And then let's see, I see a few questions. Let me see if I can pick on the last one. Yeah, I think this is a good one. Maybe Bob, if you can elaborate on that. How big is the time thermal lag? So I think what I mean is, how fast will a sensor pick up changes in fluid temperature through the tube? Okay.
So yeah, it's very fast. Well, the response time of an IRTC is 100 milliseconds. And as we showed on one of the slides, you can see the thermal resistance from the fluid to the tubing. And so there will be a little bit of a lag, but it's, a few milliseconds. So it's, it would be 100 millisecond response time still holds true. Yeah. And as you've seen on Bram's video, you can see the IRTC with the thermocouple, how it kind of matched it and it was following that. And actually, when you put a contact thermocouple in there, the response time is much slower. So the IRTC with that fast response time, even with a little bit of lag, is still going to be very fast.
It also depends on, of course, what the thickness of the wall is. The thinner the wall, the faster the sensor will pick up changes in fluid temperature. So if you want a fast response system, you need something with a thin tubing wall.
Right.
All right, well, that brings us to the end of the webinar. I hope it was interesting for you. I want to, again, thank you for attending. It's a pleasure to do this for you, and I'm really happy to see that you're all attending in these high numbers. Should you have any questions on this topic, feel free to contact us. You can find information on this on our website, and if you are interested in more information or more content, please visit our website and you can sign in for our newsletter, where we have monthly newsletters with various topics, a lot of interesting information on new technologies, applications, background information. So please sign in. Thank you all, also on behalf of Bob and the rest of our team, and I wish you all a very nice day.
Thank you, everybody. Looking forward to seeing you all and shaking your hand or giving you a hug sometime after we all get vaccinated. Thank you for your time. Thanks for attending.
Have a good day. Bye-bye.